one-sided limits and continuous functions. The limit f of x as x approaches a is not defined if its value depends on whether x tends to a or approaches a from the left or from the right. The limit of f of x as x approaches a from the left is written as the limit of f of x as x approaches a negative or a minus. So it's just x with an arrow, an a and a minus stuck on after it. And the limit of f of x as x approaches a from the right is written as the limit of f of x as x approaches a positive. So we've got x, an arrow, a, and a positive symbol or a plus after the a. Together, these are called one-sided limits. The limit of f of x as x approaches a only exists if both one-sided limits exist and are equal. The diagram opposite shows the graph of the single function y equals f of x. From the diagram, we can see that the limit of f of x as x approaches a from the left exists and is equal to 3. So we can see that if we go to a on the x-axis, we go up until we touch the graph and then across, we get to 3. That's if we're approaching from the left. So this arrow is coming from the left. Thus, we write the limit of f of x as x approaches a from the left equal to 3. Likewise, the limit of f of x as x approaches a from the right exists and is equal to 1. So if we go to a on our real axis and we go up until we touch the graph from the right hand side, so we see our green arrow is approaching a from the right, we see that it lines up with 1 on the y-axis and not 3. Thus, the limit of f of x as x approaches a from the right is equal to 1. So both limits exist, but they are not equal. As the limit of f of x as x approaches a from the left is not equal to the limit of f of x as x approaches a from the right, so basically 3 is not equal to 1, i.e. the left-hand limit is not equal to the right-hand limit, so therefore the limit of f of x as x approaches a does not exist. Existence of a limit. The limit of f of x as x approaches a exists if and only if the one-sided limits the limit of f of x as x approaches a from the left and the limit of f of x as x approaches a from the right exist and are equal. They must be the same. If asked to calculate the limit of f of x as x approaches a, we only have to check the one-sided limits if we are asked to, or we suspect that the one-sided limits are different, or f of x is a piecewise defined function with different rules for x on each side of a. The following example shows how we deal with a piecewise defined function, which is a function given by different rules on different parts of its domain. The function f of r, which maps to r, is defined as follows. F of x maps to x squared plus 3 if x is less than or equal to 1, and 5 minus x if x is greater than 1. Determine if the limit of f of x as x approaches 1 exists, and if it does, find this limit. So for x less than or equal to 1, f of x is equal to x squared plus 3. Thus, the limit of f of x as x approaches 1 from the left is equal to the limit of x squared plus 3 as x approaches 1. So what we do is we swap the x for 1, so we have 1 squared plus 3, which is equal to 4. So x values that are less than or equal to 1 include 1 and everything to the left of 1. which is why we used the limit of f of x as x approaches 1 from the left. So as x approaches 1 from the left, we're moving in towards 1. Now, for x values greater than 1, f of x is equal to 5 minus x. Thus, the limit of f of x as x approaches 1 from the right is equal to the limit of 5 minus x as x approaches 1. So what we do is swap that x for 1, so we get 5 minus 1, which is 4. So for x values greater than 1, we have everything to the right of 1. So everything approaching 1 from the right, which is why we used the limit of f of x as x approaches 1 from the right. So we ended up getting 4 for the limit of f of x as x approaches 1 from the left, and we also got 4 for the limit of f of x as x approaches 1 from the right. So as the limit of f of x as x approaches 1 from the left is equal to the limit of f of x as x approaches 1 from the right, the limit of f of x as x approaches 1 exists and is equal to 4. And the reason it exists is because we got 4 for both values. So 4 is equal to 4, so it exists, and the limit is equal to 4. So here we have a diagram or a graph to show the situation. F of x maps to x squared plus 3 for x is less than or equal to 1. So this is the graph of x squared plus 3. And this is the point 1 on the x-axis. So we see as we approach 1 from the left, we get an x value of 1 and a y value of 4. So the limit as x approaches 1 from the left is 4. And then we have 5 minus x for x values greater than 1. So here we have the graph of 5 minus x. And again, we can see that at the point 1 on the x-axis, we meet 4 on the y-axis. So as x is approaching 1 from the right, the limit is 4. So again, since they have the same limit approaching from the left as from the right, the limit of 4, the limit exists and the limit is 4. In ordinary language, a function is continuous at a particular point if its curve does not have a break at this point, not even a single point gap. More precisely, we have the following definition of when a function is continuous at a point. So the definition of continuity. The function f of x maps to f of x is continuous at x equals a if f of a is defined and the limit of f of x as x approaches a exists and the limit of f of x as x approaches a is equal to f of a. So for the limit to exist, remember, the limit of f of x as x approaches a from the left and the limit of f of x as x approaches a from the right must be equal to each other. If even one of the conditions listed in the definition is not satisfied, then the function is not continuous at x is equal to a. If a function is continuous at every point in an interval, then we say that the function is continuous on that interval. The function f is defined by f of x maps to 2x plus 3 over x minus 2. Explain why f is not continuous at x is equal to 2. So f of x is equal to 2x plus 3 divided by x minus 2. Then f of 2 will be 2 times 2 plus 3 divided by 2 minus 2. 2 times 2 is 4 plus 3 is 7 and 2 minus 2 is 0. So we cannot divide by 0, we say this is not defined. So f of 2 is not defined, and this breaks condition 1 in our definition that we looked at on the previous slide. And if any of the 3 conditions are not met, we say that the function is not continuous. Thus, f is not continuous at x is equal to 2. We may also say that the question of continuity does not arise at x is equal to 2, as 2 does not belong to the domain of f. So the domain being the x values or the inputs. The function f of r maps to r is defined as follows. F of x maps to x squared minus 1 if x is less than or equal to 3, and 2x plus 1 if x is greater than 3. Explain why f is not continuous at x is equal to 3. So when x is equal to 3, f of x is given by f of x equals x squared minus 1. So f of 3 is going to be 3 squared minus 1, which is 8. As f of 3 is defined, condition 1 in the definition is met. So the reason that we substituted 3 into x squared minus 1 is that for x squared minus 1, x is less than or equal to 3. Whereas for 2x plus 1, x is greater than 3. So we subbed x equals 3 into x squared minus 1 and not 2x plus 1. Now we'll examine the one-sided limits to see if the limit of f of x as x approaches 3 exists. So remember, in order for the limit of f of x as x approaches 3 to exist, the one-sided limits must exist and be equal. So let's start with the limit of f of x as x approaches 3 from the left. So if we are approaching 3 from the left, we are including all the values that are less than or equal to 3. So for values less than or equal to 3, we use the function x squared minus 1. So our limit of x squared minus 1 as x approaches 3 is going to be 3 squared minus 1, which is 8. So the limit of f of x as x approaches 3 from the left is 8. Now we're going to have a look at the limit of f of x as x approaches 3 from the right. So if we're approaching 3 from the right, it's all the numbers that are greater than 3. So for x values greater than 3, we're going to use the function 2x plus 1. So the limit of 2x plus 1 as x approaches 3 is 2 times 3 plus 1, which is 7. So the limit of f of x as x approaches 3 from the right is 7. And obviously 8 and 7 are not equal. So as the limit of f of x as x approaches 3 from the left is not equal to the limit of f of x as x approaches 3 from the right, the limit of f of x as x approaches 3 is not defined. This breaks condition 2 in our definition, and hence f is not continuous at x is equal to 3. So remember, if any of our 3 conditions are not met, we say that the function is not continuous. So here we have our U-shaped graph is x squared minus 1, and then our straight line is 2x plus 1. And as x approaches 3 from the left, we see that our limit is 8, or our y value is 8. And as x approaches 3 from the right, we see that our limit is 7, or our y value is 7. So clearly they are not equal, so our function is not continuous. There is a gap or a break in our function. A number of observations can be made about the functions and the corresponding curves that we have already met. All polynomial functions are continuous for all real numbers, and all sine and cosine functions we have met are continuous for all real numbers, but tangent functions are not always continuous.